Last time we looked at an introduction to determinants, so we saw what determinants were and how to calculate a determinant. Today we're going to start looking at some of the properties of determinants. So first we're going to look at what happens to determinants with row operations. Now remember, with row operations, we use that an awful lot in the previous chapter. We use them for solving systems of linear equations, and it tied into all of these properties about linear dependence and so forth. But we are also going to use row operations here and look at how it impacts on determinants. So take these two matrices, A and B. A is my first matrix and my second matrix is B, and take the determinants. I go from A to B by doing a row operation. My first row operation, I had 3 row operations. The first one was to exchange rows. So here I'm just exchanging row 2 and 3. So let's calculate the determinant of my first matrix. Now, remember my cofactor expansion. We said that you can use any row or any column and you get the same thing. So this gives me a bit of a shortcut. If I'm using cofactor expansion and I have a row or column with a lot of zeros, I can take that row or column and it simplifies my equations. So I note in here that column 1 has a lot of zeros. So I'm going to do my cofactor expansion on column 1. So what's my cofactor expansion? My determinant of A using column 1 is A11 times C11 plus A21 and so on, all of which are 0. So it simplifies my equations. So A11 is 2 times C11 is negative 1 to the 1 plus 1 times the determinant of the matrix I get when I eliminate row 1 and column 1, which is 0, negative 2, negative 2, 1. So what does that give me? 2 times 1 times the determinant. That gives me the determinant of 0 minus negative 2 times negative 2, minus 4. So that gives me 2 times negative 4, which is negative 8. There's my determinant of A. What about my determinant of B? So B is the matrix I get after I do a row operation of exchanging rows. Notice that I still have this nice property where I have a column with a single number, everything else zeros, simplifies my calculations. So it's still equal to A11 times C11, which is 2 times negative 1 to the 1 plus 1, times the determinant of, now this matrix has changed a little bit, comes that. Notice though it's a diagonal matrix, so it's a diagonal matrix, I can just multiply the entries in the diagonal to get the determinant. So this becomes 2 times 1 times negative 2 times negative 2. Multiply those all together. That gives me 8. Notice what happened here. My determinant, after I do a row operation, after I do an exchange, becomes the negative. It was 8. I do an exchange of rows. It becomes negative 8. That's the first property of how row operations relate to determinants. What about my second row operation? My second row operation says I can take a multiple of any row and replace that row with it. So here I'm taking 3 times row 1 and that becomes my new row 1. So we've already seen that the determinant of A is equal to negative 8. That's the same matrix as I had before. What about my matrix B? I still have that property that my first column is the best is a really good candidate for calculating my cofactor expansion. So what's my determinant of B? This time it's A11 times C11. So that's 6 times negative 1 to the 1 plus 1 times the determinant of 0, negative 2, negative 2, 1, which is 6 times 1 times 0 minus 4, which is negative 24. So I multiplied my first row by 3. What happened? my determinant changed by the same multiple. Multiplying it by 3 gave me my determinant of the new matrix. So when you do this second elementary row operation of multiplying a row by a constant, your determinant changes by that constant as well. Now what about the third row operation? Now here we're going to have to be a little bit careful because there's a little subtlety that you have to be a little bit careful of. So the third row operation says that you take any row plus a multiple of any other row and replace that first row. So for example, R2 minus 2R1 is the new R2. So we know that the determinant of A is equal to -8. That's the same one we've been working with. What about the determinant of B? Well, in this case, we don't have a nice column with just a single number in it anymore, but we'll still keep working with that first column. So what do we get? So the determinant, when we use cofactor expansion, is A11 C11 plus A21 C21. What's that equal to? A11 is 2, C11 is -1 to the 1 plus 1, times the determinant of -2, -2, -8, 1. The matrix you get by eliminating the first row and column. Plus A21 is -4 times -1 to the 2 plus 1 times the determinant of 1, -2, 3, 1. So what does this work out to? Well, this is 2 times 1 times, what's this determinant? -2 times 1 minus -8 times -2 plus -4 times -1 times, this determinant is 1 times 1 minus 3 times -2. So this gives me 2 times 1 is 2 times, what's in here? That's -2 minus 16, so -18, plus -4 times -1 is 4 times, here I get 1 plus 6, so that gives me 7. That gives me -36 plus 28, which is -8. Notice the determinant does not change. When you apply that third row operation, the determinant doesn't change. Which gives us this theorem, which really just summarizes those three things. So when you interchange two rows, you get the negative. When you multiply a row by a constant, you get the determinant, the original determinant times that constant. When you add a row of A to a multiple of another row, you get the determinant is the same. It doesn't change. Now here's the thing I want to warn you to be careful about. Notice this third row, this third rule. The third rule technically says that you take a row and add a multiple of another row. Now, when we're actually doing row operations, we will sometimes do something like matrix A becomes 2 row 1 plus 2 row 2 is the new row 1. That is technically not an elementary row operation. The row operation says that if you're replacing row 1, the coefficient of row 1 in your operation has to be 1. Like here, we replace row I, the coefficient of row I here is 1. When you do this, what you are technically doing is you're doing two row operations together. So this has to be, you have to be careful about this. What you're doing is you are doing the second row operation followed by the third type of row operation. So when you are doing row operations and following through for the impact on determinants, you will do things like A becomes row 1 plus 3 row 2 is the new row 1. That's valid because the coefficient of row 1, the coefficient of the row you're replacing, is 1. It can't be -1. It can't be anything other than 1. So be careful about that when you're using row operations to find determinants. So here's an example. We have this matrix, and we're saying, let's find the echelon form of A and use it to find the determinant of A. So we could calculate the determinant of A using cofactor expansion. But in this case, we're going to do something different. We are going to calculate it by reducing it to row echelon form and then using the rules for the impact of elementary row operations to find the determinant of A. So we're going to start with A being this matrix, the starting matrix. And now we're going to perform row operations. And for every elementary row operation, we're going to keep track of how it changes the determinant. So when we have A, what's a good first row operation to do? Well, we're going to get rid of everything under that initial 2. So I am going to take 3 times row 1. I'm going to take row 2 minus 3 times row 1 is the new row 2. Now notice I'm being careful that the coefficient of row 2 in this operation is 1. So I'm not subtracting row 2, I'm taking row 2 plus some multiple of something else. So my row 1 stays the same. My second row is now row 2 minus 3 times row 1. So it's 0, -3. That becomes -2 minus 9, -11, 0, -2, and 1. Now, what happened here? This is using that third type of row operation where I'm taking a row, adding a multiple of another row. That doesn't change things. So that has the impact of multiplying my determinant by 1. So the determinant of my matrix on the right-hand side here is going to be the exact same as the matrix I started with, according to the theorem that we just saw. So now let's do the next step. I am going to, let's do it this way. I am going to take 2 times row 2 is my new row 2. So 2, 1, 3. This gives me 0, -6, -22, and 0, -2, 1. So what does that have? That has the impact of what I've done here is the second row operation. I've taken a row, multiplied it by a constant. That has the impact of doubling my determinant. So let's go on again. Let's take 3 times row 3 is my new row 3. In fact, I'm going to take -3, row 3 is my new row 3. So I'm going to do 2, 1, 3, 0, -6, -22. This gives me 0, 6, -3. Now there's nothing magical about the row operations I'm doing. I'm just being very careful to limit myself to what those row operations, what an elementary row operation technically is, to make sure I don't run into that problem that I mentioned where I'm using a coefficient other than 1 in front of a row operation for that third type. So what does that do? That has the impact of taking my determinant and multiplying it by -3. Now for my final one, I'm going to do row 2 plus row 3 is my new row 3. And note that my row 3 has a coefficient of 1 in front of it. So this gives me this matrix, 0, 0, -25. Now I'm in echelon form. I'm going to call that B. So what's happened here? I've I've done a whole bunch of elementary row operations, being very careful to follow the letter of to the letter of what an elementary row operation is. Oh, and that last one doesn't change my determinant. But I've kept track at every elementary row operation of the impact it has on the determinant until I get to my row echelon form. Now my row echelon form here is a diagonal matrix, and we know how to quickly calculate the determinant of a diagonal matrix. So what do I have? I start with my determinant of A. When I went to my second matrix, I multiplied that by 1. When I went to my third matrix, I multiplied it by 2. When I went to my fourth matrix, I multiplied it by -3. When I went to my fifth matrix, I multiplied it by 1. And so that is the determinant of what I ended up with. So now let's simplify this. 1 times 2 times -3 times 1 is -6, times my determinant of my original matrix is equal to, well, the determinant of my right-hand side matrix is now easy to calculate. 2 times -6 times -25. So that is equal to 300. So now I get my determinant of A is equal to 300 over -6, which is -50. So by carefully going through elementary row operations, noting at each point how the determinant is changing, and then building this equation, I can take my easy to calculate determinant, a simple division or a simple multiplication, depending on how you're doing it. A simple calculation gets me what the determinant of my original matrix was. So that gives a connection between elementary row operations and matrices. But it also leads to another theorem, that a square matrix A is invertible if and only if its determinant is non-zero. So why is that? Well, think of a diagonal matrix or a triangular matrix. If the columns are linearly dependent, then that means we have a pivot entry in every column. In other words, that means that there is no zeros along the diagonal. What does that mean for determinants? Well, the determinant is the product of all those entries. That means the determinant is non-zero. So when a matrix is invertible, our determinant is non-zero. The other way around as well. If a matrix is not invertible, then you're going to get that the determinant is 0. So the determinant tells us whether or not a matrix is invertible. We'd already seen this for 2 by 2 matrices. It actually holds for every size square matrix. The determinant tells us whether or not it is invertible. So for example, here's another example. We have this matrix. What is the determinant of the matrix, and what's the determinant of the transpose? Well, let's take A first. Again, we have a very simple way of calculating this, but we've already calculated this. So this is the same matrix we've been seeing all along. The determinant of A is equal to -8. What about the transpose? What is the transpose? A transpose is when you switch the rows and the columns. So there's the transpose. What's the determinant of the transpose? Well, to get the determinant of the transpose, let's use the same idea, except now we have the first row is the very simple one to calculate. So it's going to be equal to A11 times C11, which is 2 times C11 is negative 1 to the 1 plus 1, times the determinant of what's left when you eliminate the first row and column. So the determinant of that. So we get 2 times 1 times, what's that determinant? 0 minus 4. Multiply this all up, and you get negative 8. So the determinant of a transpose of a matrix is the same as the determinant of the original matrix. And that's theorem 5. The determinant of a transpose doesn't change. Now let's look at another example. What happens when we multiply matrices? And this time we're going to take a simple 2 by 2 matrix as an example. So first I'm going to take the determinant of A. We can calculate that easily. This is, well, we can note that A is a triangular matrix. So it's 2 times 1, so it's equal to 2. Determinant of B, well, a little more complex, but not too bad. Negative 2 times 4 minus negative 1 times 3. You add those up, you get negative 8 plus 3, so you get negative 5. So that is the determinants of A and B. What about the determinant of A times B? Well, first we have to figure out what A times B is. So 2, 0, 3, 1 times negative 2, 3, negative 1, 4. And we have seen how to do matrix multiplications. So this is 2 times negative 2 plus 3 times 3. Below it is going to be 0 times negative 2 plus 1 times 3. Moving over to the next column, we get 2 times negative 1 plus 3 times 4. And we get 0 times negative 1 plus 1 times 4. So figure all these out, we get negative 4 plus 6, so that gives us 2. Oh, sorry, that's negative 4 plus 9, that gives us 5. We get 0 plus 3, gives us 3. Next one gives us negative 2 plus 12, is 10. And we get 0 plus 4, which is 4. Now what's this determinant? Determinant of AB is equal to 5 times 4 minus 10 times 3, which is 20 minus 30, which is negative 10. Note, negative 10 is equal to negative 5 times 2. When you multiply matrices together, the determinant is the product of those two determinants. So we note here that the determinant of A times the determinant of B is equal to the determinant of AB. Now that's just for this example, this simple example, but that holds true for any square matrices. Which is theorem 6. When you multiply matrices together, the determinant that you end up with is the determinant, the product of the determinants of your original matrices. Another important property of determinants. So we've seen a few properties of determinants. Determinants are used a lot throughout mathematics and through other sciences. They have a lot of nice properties. They inherently contain a lot of description, a lot of properties of those matrices without having to use the large matrices themselves. So knowing these properties gives you a good handle on some of the things that are going on in matrices when you multiply them together and so forth.